announcement. Yesterday, the local organizing committee has introduced a number of minor changes in the schedule. Namely, 2 couples of domestic talks were interchanged. As regards the talks of remote speakers, the times for them has remained unchanged. Now, let us proceed to the first talk. It is entitled Automatic Differentiation with Higher Infinitesimals or Computational Smooth Infinitesimal Analysis of In-Weil Algebra. The speaker, Hiromi Ishii.
Yes, I'm here.
Yes.
Can you hear me?
Yes, yes. We see you well, and we hear you well, so you can start your presentation.
Thank you. Okay, so first, I want to share my display, and it seems that the host disabled the screen sharing. So please, would you mind first to enable me to share my screen, please? Oh.
Yes, yes, please switch on.
It seems that I can't share my screen due to the current setting of organizers.
Ну, я объявил, что изменений никаких не будет. А? Ну, вот этот, вот он. Но почему-то у него он не включается.
Сейчас включат.
Ага.
Мне кажется, что
да, согласен. Ну, что-то у него там. Или они включат.
Hiromi Ishii, это она.
Она?
Ishii, да.
Yes. Finally, I get capable of screen sharing. Thanks for the coordination. So, okay. So, I'm just sharing the screen of my talk. So, okay. It seems it seems appearing on the screen. So, okay. I'm starting right here. Okay, so first I want to thank the organizers for their effort to make this conference in the hybrid form. So under the severe situation of pandemic, and I'm currently working for a private company with outside the academics. So this form also some kind of comfortable for me to be able to attend the conference remotely. Okay, by the way, so today's topic is automatic differentiation with high infinitesimals or computational smooth infinitesimal analysis in algebra. So, okay, so today's topic in short, so our contribution is to implement computational higher infinitesimal analysis, utilizing the connection between automatic differentiation and nilpotent infinitesimal analysis, applying Glebner basis technique. So what does this exactly mean? So automatic differentiation is a collection of methods to efficiently compute higher derivatives of the given function exploiting chain rule. And nilpotent infinitesimal analysis is analysis using nilpotent infinitesimal such that it's not zero, but if we square it, it becomes zero. So this is analysis in the era of Newton or Gauss. And we already know that such an infinitesimal real contradicts classically in classical logic, but it can be justified with some topos theory and used to develop differential geometry. So such an infinitesimal is used in synthetic differential geometry by Robert and others. And such infinitesimals can be algebraically formulated as by algebras. And our result is combining Grabner basis and automatic differentiation. We propose an algorithm to achieve infinitesimal analysis with general higher infinitesimals associated with Bayer algebras. So we first explore the exact connection between automatic differentiations, AD for short, and nilpotent analysis. So this is the outline of our talk. So let us first briefly review the automatic differentiation, especially forward mode automatic differentiation. Okay, so there is 3 ways of differentiation, computing differentiation on computers. So one is automatic differentiation that calculates differential coefficients efficiently and precisely using chain rules, and numerical differentiation places limits with small reals, and this is efficient but only an approximation, and symbolic differentiation that expresses function as some symbolic ASTs, abstract syntax trees, and then differentiates them symbolically. And this is exact but easy to explore exponentially with some hacks to reduce. And the method of our interest in this talk is automatic differentiation, especially forward mode. So basic idea is to store the value and differential coefficient simultaneously. And so here, the real part corresponds to the value, and infinitesimal part stores some differential coefficient. And so a pair of some 2 double values. So we use shorthand x plus yd for ADXY. So this forward mode automatic differentiation is somewhat known for a long time, and so we could implement this forward mode AD for any univariate smooth function f. So it's lifting to this AD type by regarding inputs of x plus yd as some the pair of direct value of the function and its first order derivative for some value x for some function f at some value x, and lifting of capital F should return the value of composite of large F and its derivative. So the differential of capital F at x equals a will be the coefficient of d in f hat a plus d, and here a plus d corresponds to the differential at x equals a of identity function. So this is rather well-known technique that here for comprehension I want to we will turn to some demos. So okay, Okay. Oops. And okay, I'm switching the okay, so meaning okay, how can I switch the window? Okay, it's on my okay, I found it. Okay, so there must be another. It's okay. Oh, here's the demo. So AD is a pair of real and infinitesimal coefficients, and it is implemented using linearity and Leibniz rule, and some floating point functions can be is implemented according to the chain law and their derivative rules. So, for example, if we want to compute cosine x, the derivative of cosine x plus sine x, then at pi divided by 4, we can just let x to be pi over 4 plus d. Then it returns the expected value as in d. So if we manually differentiate it by this expression and put pi over 4 into it, so they have the same coefficient as d. So and the direct value is stored as real part. So this is automatic differentiation in the forward mode in a nutshell. So okay, so we return to the presentation. So why does this work? So here we can justify this implementation with the concepts of C infinity ring and Weil algebra. So let's turn to these concepts. So forward mode AD corresponds to the dual numbering, which is denoted RD, where is the Rx modulo x squared. So which has the canonical C infinity ring structure, and as the this relation indicates, the law d squared must be 0, characterize the forward mode automatic differentiation. And C infinity ring is what is C infinity ring? So it is a commutative ring where the product preserving map AF for A to the N to A is defined for any smooth function NRE smooth function F. So a C infinity ring is a commutative ring in which smooth multivariate function naturally lifts to A. So this can be made rigorous using categorical definition, but the intuition is this. So typical example is the ring of the real values smooth function on the manifold M, and also as I stated here, dual numbering a dual numbering RD is an instance of Weil algebra, and Weil algebra is a special class of C infinity ring, which formalizes this nilpotent real line augmented with nilpotent infinitesimals. So there is another example of C infinity ring. This is so for example, the ring of multivariate formal power series, it has the structure of C infinity ring by a Taylor expansion at 0. So and this example of multivariate formal power series rings really canonical and very universal example. And another class of C-infinity ring is, as I said before, Weil algebra. And Weil algebra is an R vector space W where there exists an ideal, a polynomial ideal such that R over the quotient of polynomial ring over I is isomorphic to W, and the ideal span generated by all variables is nilpotent with respect to I. So the Weil algebra is formalizes real line augmented with nilpotent infinitesimals. So here x1 to xn play some role of nilpotent infinitesimals. So specifically, it is a finite dimensional of the de facto space. So hence I is zero-dimensional ideal. And Weil algebra is C-infinity ring because for any ring theoretic ideal I on the C-infinity ring A, its quotient, its ideal quotient has a canonical C-infinity structure induced by the quotient map. So since if W is Weil algebra expressed by Rx or by I, then I is since I is zero-dimensional, the quotient of formal power series ring by I is isomorphic to the quotient of polynomial ring. So in particular, your number ring is also a C-infinity ring by this lemma 1. And C-infinity structure of your number ring, it coincides with the implementation of forward mode AD. If we calculated the structure, C-infinity structure by forward power series ring, so the invariant case of forward mode automatic differentiation is indeed the special case of C-infinity structure of R of D. Okay, so as a summary, automatic differentiation is a method to compute differentials of composite functions of smooth maps efficiently and precisely by storing the direct value and differential coefficient at some point simultaneously. So, and this can be built as utilizing the structure of C-infinity ring on the dual number ring. And the dual number ring is an instance of Weil algebra, which axiomatizes a real line with nilpotent infinitesimals. Okay, so this is justification of forward mode AD in terms of C-infinity rings and Weil algebras. So it's time to our contribution for computational higher order infinitesimals analysis with higher infinitesimals with Weil algebras. So why we need to, we mentioned Weil algebras, why we have referred to Weil algebra and C-infinity rings instead of just saying forward mode AD can be justified by theta expansion of smooth maps. So this is because we want to generalize forward mode AD to multivariate and higher order differentials and higher order nilpotent infinitesimals. So we can achieve higher order differentials. We can compute higher order differentials with Weil algebras. So especially a tensor of the dual number rings can be used to compute higher derivatives. So if you let R d1 to dn to be the tensor product of n copies of dual number rings, then by an easy induction, we have, if we put univariate function f and lift them to up to this structure, this Weil algebra, and put and evaluated the value at x plus d1 plus blah 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 plus dn, then we have this equality. So this equation tells that we can get k's derivative of by looking at the coefficient of the product of d1 to dk of this value. So in particular, this algebra has all the information of derivatives up to the n's. So likewise, higher derivatives of multivariate functions can be computed by a finite tensor products of the dual number links. Okay, so it seems that I have 50 minutes, so I think I can do some demos. Okay. Let me see. So here's a demo. So let's calculate the easy differential coefficients of sine of half the x times e to the x squared at x equals pi over 4 up to the fourth differential. So f, and this computes differentials up to 4 differentials of this f up to f the fourth at the x equals pi over 4. And this is the table for these derivatives. And we could and next we could we confirm that this value is also computed by this tensor product algebra. So let's compute. Let's evaluate this f with this infinitesimals. Then we get this result, and it is rather hard to follow directly, so we could make this into the table. And here is the result. And comparing these tables, it seems they have the same, almost identical values. So we could, actually we could compute higher derivatives using using tensor products of your number links. Okay. Okay, so here this is where our contribution can take place. So the structure, so to achieve such a computation we have seen in demo. So our contribution is the generalization of forward mode automatic differentiation using Weil algebra. So the structure of Weil algebra is completely determined by this I, such that the ideals generated by all the variables is nilpotent with respect to I, and W is a finite dimensional vector space, and hence I is zero dimensional. So we can employ Glebner basis algorithms to compute our algebra structure. And for C infinity structure of of W, we can first calculate in the formal power series ring and cut off at the appropriate degree and take the quotient map. So first compute, and in this way, we can do the calculation in the space with general nilpotent infinitesimals on computers. So what you have to do is, so first we have to test if the given ideal actually defines the Weil algebra or not. So the first we have to have some test for Weilness. So algorithms are the algorithm one that you test is such a test. So this is just this accepts as polynomial ideal I as an input, and if I is not zero-dimensional, then returns no, and if it's zero-dimensional, it's the ideal, the radical of I can be efficiently computed with Grabner basis with well-known method, and we can test if all the variables belongs to this I radical, and if they all belong to if some of them doesn't belong to this radical, so algorithm must return no, because they are not there is not nilpotent infinitesimal variable, and all the variables in radical, then it must return the monomial basis for W over I, and upper bound of multi-degrees in I, and the multiplication table for the use in the succeeding in other algorithms. So with this information, algebraic operations on Weil algebra W is easy, and in a paper we also return the expression of non-trivial monomials, so non-vanishing monomials respect to I as a linear combination of basis for the sake of infinity, if it's for the efficiency. So with this, we can compute the infinity structure of the algebra as follows. First, lemma 1 tells the infinity structure of the algebra is given by the quotient that of formal power series Ming, and theorem 2 tells that infinity structure of formal power series is given by Taylor expansion. So we need an arbitrary partial derivatives of composite functions to compute this structure. And in general, automatic differentiation
Hiromi,
calculating.
I'm sorry, you have only 2 minutes.
Oh,
2
really?
minutes.
Oh, okay. So we can use this. We can compute this by this duration. And using this, the calculating Weil algebra, the infinity structure of Weil algebra is just an easy task. So with this, we can, for example, we can use higher infinitesimals for more efficient computation of higher order derivatives than tensor product approach. So we can use this algebra instead of n tensor products for efficiency, and it is efficient in terms of both memory and time. So, and we can also provide some specialized implementation for tensor algebras as using convolutions. Okay, so I skipped demo, and okay, so here's a summary. So fourth model automatic differentiation responds to the nilpotent infinitesimal analysis of second order, and this can be justified by the theory of infinity rings by Lover and others. And fourth model AD is an instance of Weil algebra which has nilpotent infinitesimals, and our result combines AD and algorithms for zero-dimensional ideals and achieving computational infinitesimal analysis with higher order nilpotent infinitesimals on computers, which enabling us to encapsulate higher order derivative AD for higher order derivatives and combine them using tensor products. Okay. Thank you.
Thank you very much. Are there any questions or comments? Oh, he was the first.
Excuse
me, and do you find new solutions applying your methods in differential equations?
Yeah, it can compute some derivative of given equation, so it can be used to solve differential equation to use with some numerical computation, because so this is just packaging automatic differentiations in algebraic form, so it can be used where ordinary automatic differentiations, and yes, we can use this as to compute the differential coefficient at some time, and use Euler method or something others to use to numerically solve differential equations.
Thank you very much.
Is there any hope to use this approach to obtain a constructive version of Stafford's theorem for the Weil algebra?
For Weil algebra, it can be so simple for Weil algebra, for any algebra, Weil algebra, we can compute its C-infinity structure, and if we given with some functions with automatic differentiation, which supports automatic differentiation, we can compute the value of this. And if we combine this symbolic symbolic computation, then we could do this in algebra. We could compute some symbolic differentiation, symbolic expression of some derivative of functions. But for C infinity rings other than Weil algebra, it poses much challenge because other general C infinity algebra is inherently uncountable structure. So we need some restrictions on their inputs or outputs or whatever. Yeah.
Okay, thank you very much.
Are there any further questions or comments? No, then I have only one little question. So far as I understand, you can work only with the infinitely differentiable functions, yes?
Yes. So there are infinitely many differential functions, but this can be applied to some functions that is implemented as floating point operations.
Yes. And what happens if some higher derivative of the function becomes discontinuous? Then this.
Yeah. Yeah, this is a really good question. So, for example, the reciprocal function or atom function, whatever, can be still regarded as some smooth function from submanifolds to R. So if you restrict to this domain, to such domain, then it defines its C infinity functions, but it's not defined entirely on doubles. So so in such domains, ADs can ADs can work as expected, but outside its domain, it has some, it can have some value, but it's not it's undefined value. So if we can extend this method to lift Weil algebra, C-infinity structure to Weil algebra to some simple manifolds. This method can be justified. Can be used to justify such partial to justify the AD for partial functions. Yes.
Thank you. Are there any further questions or more comments? Then let us thank the speaker once again for her interesting talk.
Thank you. Thank you very much.
To the next talk. It is entitled Primitive Recursive Ordered Fields and Some Applications. The speaker is Viktor Selivanov from Novosibirsk, Russia.
Так, слышно меня? First I would like to thank the organizers of this very impressive conference for the possibility to give a talk here. And I will speak about something related to computability theory and also somehow to computer algebra, I hope. Не работает. А?
На большую, так, больше нажать. Нет, надо нажимать вот прямо туда, вот там.
Okay, so I will just use. Okay. Yeah, I can use mouse, no problem. Mm-hmm. Okay, at this slide you see the contents of my talk. First I will give some informal introduction explaining the ideas of this talk. Thank you. Then in this part I will say something about computability on discrete structures on countable number fields. And then I give some applications to primitive recursive root finding in such fields, and then slowly proceed to computability on the continuous structures like real numbers and more complicated functional spaces. Okay, so in our earlier work, we considered already computable version of our results. We studied computability. We studied computable ordered fields of reals and related them to so-called computable analysis, which deals with, informally speaking, computing on the real numbers with arbitrary guaranteed precision. A bit later in 2018, we considered polynomial time computability, which is, of course, very desirable for practical applications of our results, and that was nice, but there are only two problems. So essentially, with this approach, we can work only with fields of algebraic reals. And we would also like to work with some transcendental numbers. And the second problem with small complexity classes like polynomial times, polynomial space, and so on, is that they are usually or often are not closed under important mathematical constructions. So in this talk, we consider a popular complexity class in between polynomial time and computable, namely primitive recursive computability. And in this case, we obtain some balance between at least theoretically applicable results and just this class is powerful enough to include many mathematical constructions. So, of course, primitive recursive the class of primitive recursive functions or tasks is too broad to consider practically of any practical value, but at least it gives possibility to measure computational complexity of problems in principle, just to count steps of computations. And this is already a big progress concerning general Turing computability, which is mostly addressed in computable analysis, which is now fast developing. And in the talk of my co-author, Svetlana Selivanova, on Friday, she will speak about more practical complexity classes in the context of solving differential equations with guaranteed precision. Okay, so we were not, the class of primitive recursive functions was very popular at the early stage of development of computability theory in the 40s, in the 30s, 40s, and 50s, but, it is still popular, but only in mathematical logic in proof theory. But it somehow was out of fashion during last decades, but nevertheless, the very last years, it became popular again, just because we came up with this our results, and we were not the only ones. Such people like Bazhenov, Downing, Kalimulin, Melnikov, and Andrey also started intensively started to actively consider primitive recursive algorithms to analyze so-called online computability. Well, I will not go into detail here. Well, yeah. Yeah, just two other words. Just informally, we will in this work we will identify computational tasks which can be programmed without such bad programming constructs that while do operator while something goes on, do something, right? And this is a bad construct because you cannot estimate number of steps at all. And the same with this programming construct, repeat until. So we just completely, well, informally, primitive recursion just forbid this, such kind of unbounded search through countable structures. And in this case, I do believe that this is an important step concerning feasible algorithms. Okay, so essentially, I already commented this slide. Our results on the class of primitive recursive problems nicely complement the previous results which I mentioned about general computability and polynomial time computability. In polynomial time computability, we worked with Weil El Hajj jointly, and we hope to find something new about, say, root funding in the field of real algebraic numbers. Okay, so now I proceed to more formal part of my talk, and I start with recalling very general definition of so-called constructivizable structure. This is in Russian Novosibirsk terminology. I find it a bit maybe misleading, but nevertheless it is still used. So a countable structure of it's quite a general definition. A countable structure of finite signature sigma is called constructivizable if there is a numbering of the universe of the structure such that all signature predicates and functions are computable with respect to this numbering, so from the names of objects. And also the equality relation should be computable. So this is Russian terminology. There is equivalent American terminology which prefer to consider not numberings but countable isomorphic copies, say when structure is coded by, say, natural numbers again or by words in a finite alphabet, but they are completely equivalent. In this general Turing computability, these definitions are equivalent, but say in polynomial time setting they are not equivalent. In primitive recursive setting they are also not equivalent strictly speaking, but for the ordered fields which I will consider, they are in fact equivalent. So I will use this Russian and American terminology interchangeably. Okay, so I just this slide is too formal. I just say that the case of primitive recursive function of primitive recursive constructible structure is obtained from this definition if we just change computable by primitive recursive. So all functions or all relations on the structures should be presented by primitive recursive functions. Okay, so just skip this. So just for correctness, I present formal definition of primitive recursive functions. These are just functions on the natural numbers, which are generated from the constant zero function and from the successor function and from projection functions by repeated applications of composition, just substituting functions and so-called primitive recursive. This is an easy part of recursion. There is another characterization of this due to Raphael Robinson, a very nice characterization of unary primitive recursive function, which technically simplifies some things, and in our paper we in fact use this this characterization. Okay. Of unary primitive recursive functions. Okay. Now I proceed to the first result of our talk, and this concerns with the operator of a real closure of an ordered field. It is it is a classical result of algebra that for any ordered field an algebraic extension of this field, which is so-called real closure. So you can solve all reasonable equations just staying in the real part of the field. So, there is a huge theory of computably presented structures, and within this theory, Yershov and independently Madison long ago, in the late 60s, I guess, proved a computable version of this Artin-Schreier theorem, which says that if a field is constructivizable, so computably presentable, then so is also its real closure. The real closure is, I don't know, the real closure by A with hat. We make search for a primitive recursive analog of this Yershov-Madison theorem. We were not able to prove a complete version of this theorem, but we have found a useful particular case of this theorem. It is concerned Archimedean fields. So up to isomorphism, this is just subfields of the reals, Archimedean ordered fields, right? But not for arbitrary Archimedean fields, but so-called primitive recursive Archimedean. So this is probably the main technical definition of our work. A numbered field is called primitive recursive Archimedean. If it is computable, so it has this numbering, right, modulo which everything is primitive recursive. And there is a primitive recursive function that, given a name of any element of the fields, find the natural upper bound for this number, for the number alpha with the name n. Okay, and with this just natural restriction, we are able to prove that the following analog, the following primitive recursive version of Yershov-Madison result, that if you have a primitive recursive Archimedean field of reals, then so is also its real closure. That is the field consisting of all real roots of the fields. Okay, and the proof, a complete proof of this theorem, I hope, is contained in our paper. And it is very much in the spirit of computer algebra. So it uses some standard tools of computer algebra. Namely, we base the proof on the Sturm method of root separation and resultant calculus. Okay. So it suffices. Now we address the following important question of when you can compute roots of a polynomial by a primitive recursive algorithm. So it's the question is not obvious, because if you consider even algebraically closed field, which is computable, then you can just compute all roots of this field, just Turing compute, just making search through the structure and substituting the field. But if the field is even primitive recursive, you cannot find the roots primitive recursively. So it turns out that it is possible for some fields which we name primitive recursive Archimedean fields with splitting. splitting property is quite popular in this literature. So it's just, this is a primitive recursive ordered field of reals, such that you can just factorize unary polynomials primitively recursively. And it is important to note, it's easy but not completely trivial, that a primitive recursive field, even not an ordered field, but arbitrary primitive recursive field, has primitive recursive root finding. That is, you can find all roots primitive recursively, if and only if it has primitive recursive splitting. So one direction is obvious, but another one is not completely trivial. So we have shown that this class of fields is preserved by this operator of real closure. So if you have a primitive recursive Archimedean field with splitting, then A with hat, alpha with hat is also such a field of reals. Okay. So in these fields we can solve we can find the roots primitive recursively. And the same applies to the algebraic closure, which I denote by bar, as usual, as often. Yes. Okay, so now I slowly proceed to computability on the reals, which I announced. And this concerns with the question, what is the collection of all such primitive recursive ordered field of reals? So how to understand this, this collection? And in that old paper which of ours, which I already mentioned, we address similar question for Turing computability, and we proved the following nice fact. It's not very complicated. That it is related to the notion of computable real, or computable real or primitive recursive real. These notions are not new. They were studied in detail in the context of constructive mathematics long ago, in the 50s essentially. And so the notion is very natural. So real is computable if there is a so-called fast Cauchy sequence of rational numbers whose limit is just this, gives this number. And fast Cauchy means this inequality, just for all n. And the field of primitive recursive reals is just the same. So it's just similar, only the sequence of rational numbers should be primitive recursive. So long ago we have proven that if you have any finite set of computable reals, then you can add them to the field of rational numbers. And the resulted field will be again computable. So this is a nice fact, because in particular it shows that the union of all computable ordered field of reals is just the field of all computable reals. So it's easy. It's easy to understand at least the union of this collection. But for the primitive recursive case, the situation is much, much more complicated. So for instance, we can show, so it is only, the proof is only sketched in the text, that every primitive recursive ordered field of reals is a subset of the primitive recursive reals, but it is a proper subset, in fact. And I guess we are still far from complete understanding of what's going on. But yeah, by the previous theorem, by the this primitive recursive Yershov-Madison theorem, we do know that the field of algebraic reals is, of course, primitive recursive. It is even polynomial time presentable. But what about adding transcendental numbers? For instance, we would like to develop computer algebra algorithms, not only for algebraic reals, but also for transcendental reals like Euler number or, say, Sokal number pi, right? So what about this? So, a partial answer is given in this theorem that there is a primitive recursive Archimedean field with splitting of arbitrary transcendental degree. So you can, in principle, add even infinitely many transcendental numbers. And for those famous numbers E and pi, the result is that these particular ordered fields are primitive recursive. So, thus also the algebraic closures are so by the previous theorem, by this primitive recursive Yershov-Madison. Well, in contrast, there is a very nice question where we don't have answer. Maybe somebody in this audience know it. Yeah. Okay. Okay. So it's a very nice question whether the field of is there any polynomial time presentable field containing at least one transcendental number? So I think we are far from having an answer to this question. So I'm mostly out of time, and just only shortly I mentioned some applications to the problem of to spectral questions of finding spectral decompositions of matrices, which is of course a very important question for numeric mathematics. So we have the following proposition. If we have this primitive recursive Archimedean splitting field of reals, and if we consider symmetric real matrices with coefficients in these fields, in this field or in its real closure, then we can primitive recursively find its spectral decomposition. The same applies to Jordan normal form. We can compute Jordan normal form. And this result applies, in fact, to to numerical solving of some partial differential equations. We considered symmetric hyperbolic systems of equations studied by many people, including Sergei Godunov. This result can be used to apply some stable difference scheme to find solutions of such systems using just only primitive recursion. So this is an implication. So I just skip this and just go to conclusion. So our results, I do believe that our results stress very close interaction between seemingly quite different topics in mathematics, namely computable structure presentations, which is considered in general computability theory and recently in complexity theory with computer algebra. So, and I do have this interaction. I do think that this interaction is very fruitful in both directions. And also in the application to differential equation, we just stress that I guess the idea is not known, but our results clearly demonstrate how a symbolic computation may be used to find some some algorithms in numerical mathematics, say in solving some partial differential equations. So thank you very much.
Are there any questions or comments?
I have a very naive question to ask. Do you run into Gödel type difficulties in this theory? I mean, is there any case when it is difficult to decide whether a structure is computable or not computable, and maybe even impossible, I mean, theoretically impossible to make that decision? Does this occur in your setup?
Yes, it's a very good question, and as I said, such kind of questions are well known from the time of constructive analysis. For instance, even in the general computability, I mentioned if you have a finite set of computable reals, you can include it into some computable ordered field of reals, right? But this is not constructive. So you cannot compute from this finite set F.
Or you cannot.
The algorithms. So algorithms are not uniform.
I see.
So it's so we have already a problem of this type with. So you cannot uniformly solve, say, differential equations uniformly from this computable reals, from coefficients, say, of matrices. You cannot uniformly. But we know that algorithm does exist, but how to write it down, it's a problem because it's related with how to compute the basis of transcendence. So it's not computable, it's very well known.
I see. Thank you very much.
Any further questions or comments? Then I have one question. Our conference relies heavily on symbolic computations. As you mentioned many times in your talk, symbolic computations are implemented exactly in computer algebra systems. Now let us take the computability problem, which, as I understand, is one of the important problems in the theory of programming. Sure. And now my question, how do you think are the symbolic computations well implemented in the existing computer algebra systems? First of all, such general purpose systems as Maple or Mathematica, or you see some shortcomings, general shortcomings?
Well, I guess essentially I was talking about this in my talk. So I guess most of algorithms which were found in the theory of theory of computably presented structures, most of them are not realizable at all. But for this reason, we need to just concentrate on more efficient presentations of structures, right? So this is precisely what I was trying to explain. Yeah.
I can see that there are still a problem in computer algebra systems that some symbolic computations have too low speed or require too much memory.
Right.
So maybe general theory of programming can help in solving such problems.
Well, I'm not sure about theory of programming. Programming is, well, just writing down the algorithm. I think that in this context, just complexity theory, theory of complexity of computation can be of use. And Svetlana, I guess, will say something about that. Because they really, so for instance, PNP problem, right? It's, so it is not implementable, strictly speaking, right? But you know, there are many approaches just to try to implement it. And it is successful It is successful just practically. So there are so-called SAT solvers, right? SAT solvers, which solve a majority of problems in the application. So I think that something similar also applies in this context. So just developing techniques from computational complexity theory can help to solve many problems. But you know, it is a very technically involved field. You know, and
but sometimes the obtaining of complexity estimates in itself is a very difficult task.
Right. Say, test for primality, right? Is there a polynomial algorithm for testing primality? Just you are given a natural number and you have to say, is it prime or not prime? So it is an extremely complicated question, and it was solved only recently, as you definitely know. So, and it uses just a lot of number theory. So I think that in some of our questions concerning these transcendental numbers, also some number theoretic questions could be of help.
Thank you. Let us thank the speaker once more for his very interesting talk. Now we have a coffee break, and at 11 o'clock a.m. we will continue our session. Continue our morning session. The next talk is entitled Design of Low Artifact Interpolation Kernels by means of Computer Algebra. The speaker is Peter Karpov from Moscow.
The subject of my report lies at the intersection of computer algebra and signal processing. I shall talk about the design of kernels for image interpolation problem. And the problem of interpolation consists in reconstructing a continuous function given its samples at some specified points. And I shall talk specifically about image interpolation, in which we have uniform samples on a two-dimensional square grids. One very important class of interpolation methods is linear interpolation, which can basically be stated as a convolution of the original sampled points with the interpolation kernel. And in case of the image, the convolution can be written as this sum, where S is the original pixel image values, and psi is the interpolation kernel, the convolution kernel. And it is often convenient to work with separable kernels, which means that the two-dimensional kernel is obtained as a product of two one-dimensional kernels. It is convenient for two reasons. First, it makes the expressions themselves much simpler, and second, it allows to run the interpolation algorithm efficiently, because in this case, the interpolation can be applied along two image axes separately, first along the x-axis, then along the y-axis. But the problem with linear interpolation is that it introduces undesirable artifacts when interpolating images, and there are several types of undesirable artifacts which we want to avoid. This illustration demonstrates the nearest neighbor interpolation, and on the left you can see the interpolation kernel, which is just this rectangular function, and it introduces these blocking artifacts, or in other words, visible anisotropy caused by the fact that the grid is square and the kernel is separable, so the structure of the grid is immediately visible. Another type of artifacts is blurriness. In this case, on the left you can see the linear interpolation kernel, and on the right you can see the result of interpolation with this kernel. And this kernel has the disadvantage of introducing visible blur around sharp edges. Another type of artifact is ringing. Here you can see the sync kernel, and this kernel has very prominent and slowly fading oscillations, and they also manifest themselves on the interpolated image as visible halos around sharp edges and oscillations even far away from them. So the problem of kernel design is not a trivial one, because one has to balance different types of artifacts in order to obtain high quality visual results. Various kernel design criteria that have been employed in the literature include smoothness, because smoothness class of the kernel is an important parameter. It relates to the asymptotics of the kernel Fourier transform. So the kernels are usually required to be continuous and sometimes have continuous higher derivatives. Another criterion is the exact representation of power series expansion. So the first linear term, secondary term, and so on, and higher terms. Another criterion is similarity to sinc function. Sinc function is defined as sinus px divided by px, and it is theoretically the perfect function, the perfect interpolation kernel for band-limited signals, because it allows to reconstruct them perfectly. But in reality, it usually produces poor results, as we already saw, very significant oscillations, because real images are not band-limited. And another criterion that has been employed is the performance for a particular model of the Fourier spectrum of the signal. However, most approaches found in the literature neglect the anisotropic artifacts and also only apply to one-dimensional kernels. And in this work, the approach is to directly quantify the anisotropic artifacts and design a two-dimensional kernel that minimizes them. We start by defining the kernel itself. The kernel is defined as a piecewise polynomial function on an interval from -r to r. So there are two parameters, the support size, r, and outside of the support size, the kernels are 0. And the second parameter is the order of the polynomials on each subinterval. And there's another choice to be made, which relates to the subintervals. For delta 0, the subinterval endpoints correspond to integers, and for delta 1/2, the interval endpoints correspond to half integers. Then we define the properties of the kernel desirable properties that the kernel has to have. The first and most important is the interpolation property, because when we reconstruct the signal by convolving the samples with the kernel, we want the reconstructed signal to match our samples exactly. And this means that the interpolation kernel has to be 1 at x equals 0 and has to be 0 at any other integer x. Then we want the kernel to be continuous, because otherwise it would introduce sharp transitions in the interpolated intensity image. This criterion can be extended to higher derivatives. So an optional criterion is also used for the smoothness of the first, for the continuity of the first derivative. The next desirable property is partition of unity, which means that if we interpolate a signal that consists just of a constant value, we get a function that is identical to that constant value for any x. And it's possible to extend this property to higher orders. And the next criterion is the exact representation of the linear signal term, which means that if we interpolate a linear function, sampled linear function, we also get a linear function. it's also possible to extend this criteria to higher order terms, but that would take away the degrees of freedom, so it was decided to stop at the linear term. The next step is defining the measure of the anisotropy, the quantity that we want to minimize, and to do so, we introduce a diagonal, we consider a diagonal edge at 45 degrees that splits our image into two half planes, with one half plane containing ones, the other half plane containing zeros, and then we consider what happens during the rasterization process. And on the image you can see the boundaries of two pixels, and depending on the offset of the sampling grid, the pixel values can be different. The pixels in the rasterized image can assume 4 different values depending on the offset parameter theta. And then we can define the interpolant as a convolution of our edge image with the convolution kernel, with the interpolation kernel. And the idea of the objective function employed in this work is to quantify the magnitude of blocking by penalizing the isoline distortions of the interpolated image, because edges are a very important, play a very important role in human visual system. So we want the interpolated edges to stay straight, but this is not the case for common interpolation kernels. Here on the image you can see a vector plot of the step function introduced before. It's a vector plot of the gradient of the interpolated step function interpolated with the linear interpolation kernel. And on this plot, first you can see that the isolines are not straight, they are meandering around. And we can also see that the direction of the gradients varies significantly. And the idea is to minimize the anisotropic artifacts by penalizing the isoline distortions. And this was done by introducing the objective function that is an integral of the gradient of the interpolant, of the dot product of the gradient of the interpolant, and the vector that points along the edge squared. So in this case, if the isolines were straight, then the gradient would have been orthogonal to the vector pointing along the edge, and so this measure would have been 0. So this is the reason. So perfect blocking-free, artifact-free interpolation would have this quality score 0. And having defined our objective function, we can proceed to kernel construction. The construction process was performed in mathematical computer algebra system, and it consists of a number of steps. The first step is obtaining the equations for the constraints that define the kernel properties introduced before, like the interpolation constraint, smoothness, optionally continuity, and optionally smoothness of the first derivative, and partition of unity, and so on. In some cases, like the interpolation constraint, this is trivial. In other cases, like continuity of the first derivative, we have to first evaluate the values of the kernel at the interval endpoints at each side of each interval endpoint, and then equate them and obtain equations in this way. And then when we obtain all the equations defining our constraints, our desirable kernel properties, we solve them. It's a linear system. We solve it with solve and obtain a general solution that only contains a few remaining independent variables, the kernel coefficients. The next step is evaluating our objective function. This step is done in several sub-steps. We calculate the interpolant. We differentiate it along each axis. Calculate the dot product with the vector 1, 1, squared, simplified, and integrate. And in this step, the simplification and integration has to be done separately for each subinterval, because otherwise Mathematica just takes too long to calculate if we try to directly integrate the piecewise functions. And the integration region corresponds to a single period of the interpolant, because the interpolant is a periodic function. When we are done calculating the objective function, we find its stationary points. We differentiate it with respect to the free coefficients. We solve the resulting system of equations with solve. And finally, we verify the resulting solution. We verify that it is indeed a local minimum by checking the positive definedness of the Hessian matrix. And this is, these steps were carried out for each individual kernel, and the kernel parameters were as follows. The support size R ranges from 1.5 to 3. The polynomial power ranges from 2 to 4. So this gives us 12 parameters in total, and there's also another optional constraint, the continuity of the first derivatives. So all in all, this gives 24 parameters to which this kernel construction algorithm was applied. And another thing to mention is that we are only interested in real solutions, because solutions with imaginary parts are of no use for image interpolation. And we were able to apply this algorithm to all 24 cases, and in all cases except 2, we were able to obtain symbolic results. And in this particular 2 cases, there are 2 failure cases. In one case, the Mathematica could not solve the resulting, the final system of polynomial equations in sufficient and reasonable time. And in another case, there probably was a bug in Mathematica's solve function, because it just gave incorrect results. So in these 2 cases, the last step of the algorithm had to be carried out numerically. And this table illustrates the number of free variables for different kernel settings. You can see that in some cases the system is over-constrained. There are no solutions at all. In some cases there are unique solutions, and Actually, some of these unique solutions correspond to kernels already known in the literature. And here are a couple of examples of the objective function polynomials. The first polynomial is for kernel with support size 2 and polynomial order 2. It's a univariate polynomial, and the second polynomial corresponds to kernel of support size 3 and polynomial order 3. So this is one of the largest polynomials encountered. And here we can see the illustrations of the kernels themselves obtained through the construction algorithm for radius 3 and for radius 1.5, for radius 2 compared with the Lagrange kernel of identical size, for radius 2 with an additional constraint on the continuity of the first derivative, for support size 2.5, again with the additional constraint, and for support size 3, and again same support size with the additional constraint. And for the support size 2, the solid line is the well-known Thies interpolation kernel that corresponds to bicubic interpolation, a very popular kernel that has been implemented in various image processing programs like Adobe Photoshop and so on. And the dashed curve is the new kernel of higher order, of polynomial order 4. We can already see some differences, that new kernels have a more prominent overshoot, which normally would be considered a disadvantage because it increases ringing, but the advantages compensate for that. And here we can see the gradient of the interpolant of the diagonal edge function, comparing the popular Thies kernel and the newly obtained kernel of the same size. And we can see the differences in isolines. The isolines of the Thies kernel are very far from being straight and much closer to perfectly straight in the newly obtained kernel. And another practical test is interpolating the zone plate function, which is defined by cosine of x squared plus y plus y squared. And again, the same kernel as in the previous slide. We can see the anisotropic artifacts appearing on the Thies kernel, especially in the high frequency regions, manifesting themselves as this kind of ripple that gives away the square structure of the sampling grid. And the artifacts are much less prominent in the newly obtained kernel. And also remarkable fact that the reduction in the magnitude of anisotropic artifacts has been obtained with smaller polynomial order, because the Thies kernel has polynomial order 3 and the new kernel has polynomial order 2. And this slide makes this, again, comparison between the gradients, but now for the support size 3. And we can again see the same picture, and the isolines of the optimized interpolation kernel are very close to being straight, and this can also be seen by observing the direction of the gradient vectors. And again, comparison between two kernels with identical support size. One is a popular kernel, existing kernel from the literature, and on the right is a newly obtained kernel. And we can see that in this case, the anisotropic artifacts are eliminated almost completely. But in order to make a real-world comparison for the intended use cases, the kernels must be compared on actual images, on photographic images, because that is the purpose of this work, to make high-quality kernels for image interpolation. And we have chosen a number of kernels reported in the literature for this comparison. From the commonly, from very well known like nearest neighbor and linear, Thies kernel that's also known as bicubic image processing software as Adobe Photoshop, Lansash kernels, two versions with different support sizes, also a popular kernel which belongs to a family of windowed sync functions. Lagrange interpolators, interpolating kernels arising from classical polynomial interpolation. And finally, B-splines, which have infinite support, but considered the gold standard of interpolation because they produce high quality images, but they haven't gained much popularity because due to the infinite support, they are more difficult to implement and are more costly computationally. And in this table, we can see a summary of the metrics for different kernels, existing and new ones, the magnitude of the anisotropic artifacts, and the root mean square for the zone root mean square interpolation error for the zone plate image, and the bolded values represent the best values for kernels of smaller or identical size. So the kernels are ordered from smallest to largest, and the bold values represent the best found so far, and we can see that the new kernels improve significantly upon the existing designs. And the final step is full reference image quality assessment, because comparison of image quality is a non-trivial task, and multiple methods has been proposed for it, from the naive ones that just consist of taking the root mean square error to more complex that include structural image similarity and even deep learning approaches. And the experimental setup was as follows. We included 14 image quality assessment methods, 12 photographic test images that were downscaled and then resampled back to the original size. And here we can see in this final table the summary of the normalized image quality assessment scores. The gray bars represent existing kernels, and the colored bar represents the obtained kernels. And we can see that on average, the new kernels improve upon the existing designs and even improve upon the costly B-splines. So finally, to conclude, I'd like to summarize the results. By using computer algebra, we were able to obtain new high-quality interpolation kernel that are a large improvement in terms of both subjective and objective image quality. We were able to obtain most results symbolically. The results, the Mathematica notebooks with kernels and all the code can be found at the GitHub, and the preprint can be found at the archive page.
Thank you very much. comments? Questions or comments, please?
Is it possible to optimize kernel parameters for some class of image? For example, for class image as portrait or nature.
The kernels themselves are very small, and at this scale, I don't think that there is a significant difference in statistical properties between like portrait images and nature-based images. There would be a difference between photographic and non-photographic images. So in this case, yes, that would be indeed two different classes. But on the other hand, if you are dealing with non-photographic images, I would advise against applying linear interpolation at all.
Thank you. Thank you.
Any further questions or comments? Then I have, so to say, a comment. There are wavelet functions, which are widely used also for solving similar tasks. About 25 years ago, in all police departments of the United States were the computer programs introduced for taking the fingerprints. Why write wavelets? Because it was shown theoretically that when we compare the expansion over wavelets and the expansion in Fourier series in science, then the convergence of the wavelet series in wavelets requires much smaller number of terms. So that there is a significant economy of computer memory for each fingerprint. So that it seems to me that you could, as the next experiment, to try to use wavelets with indeterminate coefficients, series indeterminate with indeterminate coefficients, not necessarily exact expansions into wavelets. After that, one could solve the optimization problem, certain optimization, more exactly, minimization problem, to minimize such artifacts. To my knowledge, wavelets outperform significantly the sinc function which you use.
Well, I didn't really use sinc function. I just used it in comparison, to compare the new kernels with it.
Only kernel. But the final task is to get good images with very small distortions in the signal. This is an old problem which has been solved everywhere in the world by different techniques, different functions. But wavelet system was found as one of the best ones. In Moscow, there are several people in Keldysh Institute which are concerned with wavelet expansions. At the moment, I do not remember their names. They have published several years ago their paper in the journal Математическое моделирование. It is translated into English. So that was my comment. Are there any further comments or questions? If there are no further comments, questions, let us thank the speaker for his interesting talk. And now we proceed to the next talk. The next talk is from France. entitled On the Computation of Solutions of Linear Integro-Differential Equations. The authors, Moulay Barkatou and Thomas Cluzeau. But I am sorry for that, I do not know the name of the speaker. What is this? I hope we will soon see the actual slides for this talk. Moulay Barkatou and Thomas Cluzeau. Okay, we will see you well, so that you can start your presentation. But there is no sound.
But I don't know, in fact, I don't know if you hear me, I don't know if you see my slides.
We see your slide and we hear you.
Okay, so now, so I can start?
Yes.
Sorry for that. So hello everyone, so I'm Thomas Cluzeau from France, and today I'm going to talk about the computation of solutions of some linear integro-differential equations. Okay, so, sorry. Okay, so what is it about? So usually when you have linear ordinary differential equations, so something like this, you know that we have a lot of algorithms to compute many kinds of solutions, like polynomial solutions, rational solutions, or exponential solutions. And we have many algorithms that are implemented in computer algebra systems like Mathematica, Maple, or other ones. So now the idea of this talk and what we are trying to do is to consider integro-differential equations. So now you have differential terms, but you also have integrals in your equations, and you want to do the same. So you want to develop and implement algorithms for computing solutions. So in this talk, I will mainly consider the computation of polynomial or rational solutions of these linear integro-differential equations. Okay, so this is the goal. So let us start with some algebraic setting to clear, so that everything is clear. So when you consider differential operators, so you are in what is called the first Weil algebra. So you have a field of characteristic 0, which is capital K in my talk. You can think of K to be the field of rational numbers, Q if you prefer. So this will be the polynomial K algebra in one variable, x. And this set will be the algebra of endomorphisms of K of x, which means K linear maps from K of x to K of x, okay? And the first Weil algebra, which is also called the algebra of differential operators, is the subalgebra of this algebra, which is generated by three elements, the identity x, which is just the multiplication of a polynomial by x, and this partial d, which is just the operator which differentiates a polynomial. Okay? So you consider the subalgebra of all the K linear maps from K of x to K of x, which is generated by these three elements. So of course, you know that you have the so-called Leibniz rule, which says that if you multiply by x and then you differentiate, it's the same as differentiating, multiplying by x, and adding the function. So you see from this Leibniz rules that this algebra is non-commutative, and you are in a non-commutative world. However, you see from these Leibniz rules that when you have a term like d on the left and x on the right, you can always pass the x on the left and keep the d on the right. So it's more or less clear, and can be proven easily, that the normal form, so every element of this algebra of linear differential operators can be written like this L in red at the end. So you have a double sum of coefficients, which are in K, powers of x on the left and powers of d on the right. Okay, and every linear differential equation can be written like this. Everything is clear in this setting. Now, I come to the algebra of integro-differential operator. So now I consider the sub-algebra of this end endomorphism algebra of K of x generated by the three elements 1, x, and d. But I add also this operator, integration operator, which maps a polynomial p to the integration of p between 0 and x. Okay? So I have the three operators 1, x, and d, and I add this integral operator. So now inside this new algebra, I have many other formulas. For instance, the fundamental theorem of calculus say that if you integrate and then if you differentiate, then it's the identity. You also have the formula of the integration by parts that can be written like this, in these operator settings. And for instance, you have the evaluation at 0. So if you take the identity minus the integral of the derivative, and if you apply this operator to a polynomial p of x, you will get the value of p at 0. Okay? And so I will introduce in the following, and I will not it like this in the following. So this evaluation operator at 0, so 1 minus the integral for times d, I will call it E, like evaluation. So remember, it's the operator that take a polynomial and evaluate it at 0. So now, an important question when you are in this ring is what is normal form of an element of this ring? So it's less clear than in the differential case. And remember, in the differential case, you have this Leibniz rule. So every x can go on the left of d. So it's clear that we have a normal form like this. Here it's more complicated. So you need to see how all these formulas go together, and when you are given a linear integral differential operator, how can you write it in a normal form? So this has been investigated by Regensburger and Rosenkrantz, and they have proved that every element in this algebra can be uniquely written in the following normal form. So you have, in fact, a sum of 3 terms. So you have a term which is a purely differential operator, like before. You have a term, which I call the integral term, which is something like this, the second term. So you see that in this term, you have an integration operator, just one. You have a power of x on the right and a power of x on the left. And you have a third element of the sum, which is an evaluation operator, which is something like this. So you have a power of d on the right, you evaluate, and you multiply by x. Okay? And they have proved that every linear integral differential operator can be written as a sum of 3 terms like this, which means that every linear integral differential equation can be written like this, what it is written at the end of this slide. Okay? So that things becomes clearer. You have a term, what is an integral differential equation? You have a sum of 3 terms. So one term d, it's a differential term, so it is something like this. Usually you have something like this, you see, differential equation, like before. You have an integral term. So in this integral term, you have power of x on the left of the integration and powers on the right. So you get something like this. So you have term like this when you have an integral differential equation. Okay? And then you have the evaluation part. So you also have terms like this. So you differentiate, you evaluate at 0, and you can multiply by polynomials in x on the left. Okay? So an integral differential equation, in fact, it's a sum of 3 terms: differential term, integration term, and evaluation term. And so the goal is now you are given something like this and you want to compute solutions. Okay? So for the computation of solutions, I already said there are many works concerning just the case of ordinary differential equations. But if you consider integral differential equations, there are few works considering the computation of solutions of these equations. So there is a work by Quadra and Regensburger where they show how to compute annihilators in this algebra of integral differential operators. And they show that they can compute annihilators by computing polynomial solutions. So they say that when you have an integral differential operator, in fact, it is what is called a rational initial operator. And from this, you can compute a degree bound for the polynomial solutions, and then you can compute the coefficients by linear algebra techniques. I will come back to this later in my talk. And our ongoing project is to develop and implement efficient algorithms for computing many kinds of solutions. So it's an ongoing project. So in this talk, I will only talk about polynomial and rational solutions, but we aim at generalizing these things to compute more general solutions. Okay, first remark regarding solutions of these integral differential equations. If you look at the terms in red here, both terms in red, you can see easily that if you differentiate the good amount of times, you will get something which is a differential operator. If you differentiate g plus 1 times this element, you get something, the integral term will disappear, and you get something which only involves derivatives. And here you have these are constants, evaluation at 0. This is a polynomial of degree j, so if you differentiate j plus 1 times, you get 0. So what is the consequence of this first remark is that if you denote by r the maximum of the ei's and the fi's, so the ei's are here, these are the degrees, which maximal degrees of x that you can have here, and the fi's are here, so these are the maximum degrees that you can have here. And so from the previous formulas, if you differentiate, if r denotes this plus 1, the plus 1 which is there, and if you differentiate r times your integral differential equation, you will get an ordinary differential equations, okay? And the order will be the order of the differential equation at the beginning plus the number of times you differentiate. Okay, so this is the first remark. When you have an integral differential equation, you can differentiate and get just an ordinary differential equation. This is what you learn to do in school when you have the equation of an RLC circuits. Usually we differentiate to remove the integral term and you consider the linear differential equation. Okay, so from this first remark, we can say that the solution space of an integral differential equations will be a k-vector space of dimension at most n plus r, because you know that the solutions of the integral differential equations are among the solution of the differential equation you get when you differentiate r times. So here are small examples to illustrate these things. If you consider this integral differential equation, so you have an integral differential term, an integral term, and an evaluation term. So in this case, the order of the differential part is 1. R is 1, because there are no powers. And so if you differentiate 1 time this equation, you get this equation, just a differential equation. And you know that the solutions of this equation are cos and sine. And here you can check that both cos and sine are also solution of the integro-differential equation, which is there. So the bound n plus r, which is 2 here, is obtained in this case. But be careful, if you now remove, you consider the same equation, but you remove the evaluation term. Okay? So n and r are still 1. You still differentiate one time, you get the same differential equation. But here, the solutions are still cos and sine, but here only cos is a solution of this equation. Of course, the solutions are among the solution of the differential equations, but not all solutions of the differential equations are solutions of the integral differential equation. So these are two small examples to illustrate this fact. Okay, so now I will consider the problem of computing polynomial solutions. Okay, so I want polynomials that are solutions of my integral differential equations. So of course, you can say, okay, I know that if I differentiate, I will get an ordinary differential equations. I have many algorithms to compute polynomial solution of ordinary differential equation. I use them, and I check among the polynomial solutions of the differential equations, which ones are still solutions of the integral differential equations. So you can do this. Here is an example. You consider this integral differential equation. So you have no integral term, but you have something which is an evaluation here. Okay. So in this case, n is 2 and r is 2. So you differentiate 2 times, and you will get this very simple linear differential equations. So here the solutions are clearly all the polynomials of degree 3 or less. But if you plug this polynomial in the integral differential equation, you will see that C2 has to be 0. So you will see that the polynomial solution of the integral differential equation is just something like this. So you have 3 linearly independent polynomial solutions, 1x and x to the 3. Okay? So what you see in this example is that here, in fact, the fact of differentiating 2 times, you get this equation. So in fact, you just know that the solutions are polynomials of degree less than 3. So in fact, it just gives you a bound in here. Okay? And another point is that if you do this for a bigger equation, then the coefficients, the order and the degree can become larger. So we are interested in our work to have direct methods to treat directly the integral differential equation without transforming it into a differential equation to prevent the growth of the coefficient and the fact that once you have the polynomial solution, we still need to check. And in fact, in practice, this is sometimes easier to consider directly the integral differential equation. Okay, so I will consider directly the integral differential equation. So the first task, if you want to compute polynomial solutions, is to find the degree, as for differential equation, of possible differential solutions. So to find the degree, there is a classical technique that we can use, is that you search for a solution like this. You want to know what is capital N. So you will plug this in the integral differential equations, and you will look for conditions on N. Okay? So to do this, you need to see what are the actions of the 3 operators on the powers of x. Okay? So this is not complicated. So for the differential term, you just do the computation and you get this. For the integral term, you do the computation and you get this. And for the evaluation term, it's a little bit different because you are differentiating and evaluating. So things are a little bit different. So what you can see here is that for the differential part and the integration part, when you do this and you apply the operator to x to the k, you have sums of power x to the k plus something, x to the k plus something. But you see that for the evaluation operator, this is not the same. So it will be something a little bit different. So this is why we will put together the differential and the integration part and consider the evaluation part separately. So the first thing we do is that we consider the differential and the integrable part, and we will decompose this part. So what are we going to do? We have seen that when we apply a differential of an integrable integration operator to x to the k, you get x to the k plus something. So you will see that you will decompose this sum of two operators into another sum of operators, but for Li, when I apply it to x to the k, it gives k plus I. And before here, you will have a rational function in k, okay? Which means that when you apply this to a polynomial p of x, you will get a sum like this of coefficients p times rational functions alpha i's x to the k. So this will be explained in the following example. So it's simple. You take this differential operator and this integration operator. So here you see that if you apply this to x to the k, so you look at d2, you will get x k minus 2. Okay, so you will have something with minus 2. If you get d and x2, it will be minus 1 plus 2, so you will get something plus 1, so L1. And if you look here, it will give also plus 1 with a minus integral, and x integral x plus 1 plus 1 plus 1, so you will get something with plus 3. So you decompose L into a sum of three operators, L minus 2, which is D2, L1, which is x2 d minus integral, L3, which is x integral x. And you have these formulas. Okay? So this is just the decomposition that we usually do for differential operator when you want to do the same thing. So in fact, here I do it with the integration part, but there is no differences. And here you will get that L of P of X has an expression like this. And of course, this is important. Why am I doing that? Because I want condition on the degree n. So I want to know what is, when I apply L to P of X, what is the term with highest degree, because it will give me some conditions on n. So this is for the differential and the integration part. So for the evaluation part, this is a little bit different, as I said, and this is something that is not appearing for differential equations, so something new for integral differential equations. So when I apply it to a polynomial p of x, I will get an expression like this, and I can also write it like this, okay? But I will not get the same as for the differential and the integration operator. So for example, for instance, if I consider this evaluation operator, okay, if I apply it to every polynomial p of x, of course, as I differentiate here 2 times and I evaluate, here I differentiate 1 time and evaluate, here I evaluate, you will remove all terms of degree more than 2, because they will vanish, and you will get an expression like this. Okay? So it is. So now I put the two things together. So, and if I apply L to a polynomial p of x, I have this sum. Okay, this big sum of 2 terms. And the question is, what is the highest degree term here? Of course, here it's for k equal n plus b, and here it's for k equal n. So you will have to compare n plus b and m. So if n plus b is strictly greater than n,
recording in progress,
the highest degree term is in the first sum, and it's alpha b capital N p n x n plus b. Okay? What does it mean? It means that if you want p of x to be a solution, so if you want L of p of x to be 0, then alpha b of n should be 0. So n has to be a root of the numerator of alpha b. Okay? Remember that alpha b is not the polynomial here, but a rational solution. Okay? And the other case is when this inequality is not satisfied, which means that n is smaller than m minus b. So if I denote d the largest non-negative integer root of alpha b, then an upper bound for the degree of polynomial solution is just given by the maximum of d and m minus b. So if you know what happens for differential equations, this is the same, except that you do not have this m minus b here, because this m minus b comes from the evaluation term, which is a little bit different here. Okay? And in fact, you can know, as for differential equation, exactly, this is a bound, and you can know exactly what are the possible degrees, in fact, which is can be interesting in practice. So example, if I consider this integral differential operator, if I apply L to P of x, I get something like this. A is 1, B is 1, M is 0. So you look at this rational function here, and you look at the roots of its numerator. So the roots of the numerator as minus 3, minus 4 and 3. So the degree bound is the max between the biggest root, which is 3, and m minus b, which is minus 1. So it's 3. Okay? Here, this is given by the highest root of this element. But here, if you consider this integral differential operator, you can prove that L of P of x can be developed like this. So you look at the roots of n times n minus 1. This is not difficult. These are 0 and 1. And the degree bound is the max between 1, which is the biggest root, and m minus b, which is 3 here. So you see
I am sorry, you have only 10 minutes left.
Sorry?
10 minutes for you.
I still have 10 minutes, you say?
Yes. Well, only 10 minutes at your disposal, because the duration of talk must be 30 minutes.
Okay, I continue. But I started 10 minutes late, so I think I still have 5-10 minutes or something like this.
And if you can, please shorten your presentation
Okay.
To some extent.
Okay, thank you.
Prepare too many slides.
Sorry? Sorry?
You have prepared too many slides for your...
I don't know, but at the end I will skip some ones. Do not be afraid about this. I finish with polynomial solution, and then I just say some words about rational solutions I can skip. So many of them. Do not worry about this. Okay. So what? Okay. So I was saying that in fact here, what you find is that the degree bound here is given by 3, which is not a root of n times n minus 1. Why am I saying this? Because this is very different from what happened for a differential operator. Okay? Okay, so now with these results, I know how to compute a degree bound. So when I have a degree bound, what is usually done is that you plug this polynomial, you know, capital N, in the integral differential equation, and you will get a linear system to solve for the coefficients. So you plug it, and you have a linear system like this, okay? And you solve the equation for the PIs, and you compute like this the polynomial solutions, okay? And you can have some improvements as for differential operators. I will not detail this. I will just explain how it works on my examples. So remember, this is the same examples are before. So here the degree bound was 3. So you plug a polynomial of degree c in the equation, and you will get these linear systems for the PIs. You solve it, and you get this solution. For the second one, you have this operator. The degree bound was 3. So you plug a polynomial of degree 3, you get a linear system of equations for the PIs, you solve it, and you get things like this. Okay? And you see that here x3 is a solution of the operator, which is important because it was the degree bound was 3, and it was not a root of the initial equation at infinity. Not really this, but this is different from the differential case. Okay, so this is a classical technique to get the polynomial solutions. The other technique that we can get, and I will not give the details on this, is a monomial by monomial approach. So it has been developed for differential equations, and it can be generalized for integral differential equations, but we need to pay attention of the evaluation term. Okay, so this is just as before, except that capital N has been replaced by mu. So these are the formula as before. So we'll take SL to be all the, in fact, order of differentiations that appear after the evaluation term in the evaluation part. Okay? And for every I in SL, I will get the maximum of the degrees of the xi's that are on the left. Okay, so these are sets that you can have easily from the equations. And here, if you look at L applied to x to the mu, there are three cases. So you have one case like this when you get this, one case here when you get this. Okay, so you just have a look. And here, there is a new term which will be important for the method. So why is this term important for the method? Because in this case, the monomial by monomial approach is based on the fact that when we apply the operator to x to the mu, you get something of degree lower or equal to mu plus b. But here, in this case, this is not the case, because you see S mu is strictly greater than mu plus b. So for integral differential operator, you can have this, that when you apply L to x to the mu, you get something of degree greater. This is a new phenomenon. So we will consider these monomials apart from the other ones. That's why we define these sets of integers satisfying these conditions. Okay? And once you have understand this, you will adapt the classical monomial by monomial approach, because you will separate your polynomial solutions into two parts. One part which are the monomials that are not problematic, and another part which concerns the problematic polynomials. Your equation L of y equals 0, you will write it L of p of x equal b of x, so right-hand side, and the right-hand side is just minus L applied to this part. Okay? And the outline of the method is that you will compute one by one the monomials c x mu plus something of degree smaller. So you will need at each step to find if there exists c and mu such that L of p is b with degree of q less than mu. If we succeed, you start again with a new equation and you continue until you cannot find c and mu. And then you have a polynomial solutions if and only if you have this equation. Okay? So here I explain how I can compute c and mu. I will just give you an example to explain you the method without giving the details. So I am given this linear integral differential operator. Okay? So I can apply the differential and integral part to x to the mu. I will get that a is 2, b is 2. SL, what is SL? So these are the orders here, 3, 1, and 0. Okay? The degrees, 1 for 3, 4 for 1, and 3 for 0. So you compute this. So SL bar will just be 0 and 1. So the forgotten, if you want monomials, here are x to the 0 and x to the 1. And you can see that if you apply L to x to the 0 and x to the 1, you get something of degree bigger than 0 plus b, which is 2, and 1 plus b, which is 3. Okay, this is why they are problematic. The roots of mu and mu minus 3, which are not in SL bar, so the roots are here, 0 and 3, so there is only 3. Okay? I search for polynomial solutions like this. So these are the forgotten monomials. And instead of writing L of y of x equals 0, I write L of p of x equal minus L of p0 plus p1 of x. I have this equation. Okay? And then, step 1, I search p of x of this form. Okay? I write the equations for L q1 of x, and I look for the conditions. Here, in fact, I have three cases. So here I can look at this and say, okay, the only possibility is mu1 equals 3, and c1 can be an arbitrary parameters. Okay, so I plug this, and then I write this q1 like this. And I do the same. I look at the equation for q2. For the equation for q2, I get this. I look at the degrees, what is the biggest degree, and I'm trying to find the value of mu2, which give what we want. Here I find that the possible degree for the possible value of mu2 is 2. Okay? And with the possible value of mu2, which is 2, I look that if I want the degree to become smaller, then I need to have this equation. So C2 has to be 1/2 of P1. Okay? I continue like this. Next step, I find that mu3 has to be 1, but 1 is a forgotten monomial. X to the 1 is a forgotten monomial. Remember, it was 0 and 1. So the process ends. Okay? So now I put everything together, and I get that these polynomials satisfy the equations if and only if P0 equal minus P1. And I get the general solution, which is this one. So this is, if you want, an adaptation of the monomial bimonomial method, which exists for differential equations, taking care of some forgotten monomials. And I have implemented this in Maple, and we can see that this is very efficient to compute polynomial solutions of integro-differential equations.
I'm sorry.
I'm almost done.
Please omit some mathematical details and come to conclusions, because you have only about 3 minutes.
3 minutes? Yeah,
3
okay.
minutes for
yeah, okay.
Because you have already exceeded 30 minutes.
Okay. I finished. I just say 2 words on rational solutions and conclusions. So for rational solutions, there are 2 things. There are 3 things. There is the denominator to be computed. There is a bound for the order of each irreducible factors of the denominator, and then polynomial solutions. Okay? So here it is exactly the same. So the first thing is, what are the irreducible factors that can appear in the denominator of a rational solutions? So here you can use the fact that if you differentiate, sometimes you get a differential equation, so you know what are the possible irreducible factors. So if there is a differential part, this is clear that you will get exactly the factors of a(n) of x. But if you do not have any differential part, like for this operator, then if you differentiate, you can in fact compute a polynomial b of x, which also contains the irreducible factors of the denominators. Okay, so this is not difficult to see that if you compute this polynomial, you will get it. Okay, so this is for the denominator. Now for the order of an irreducible factor, x minus x0, then you will do exactly the same as for polynomial solution. You will plug something like this in your equations, and you will look at the lowest order term. You will get some kind of initial equation. So I will not give the details here, but once again, the problematic part is the evaluation part. So for the differential and integral part, you get something like this. Okay? And this, guys, comes either from the differential part or for the integrable part or for both of them. And for the evaluation part, you get something like this. So you see that once again, you need to compare minus k minus a to small m. And you get a bound by taking the maximum of the smallest negative integer root of alpha minus a and minus a minus m. So this is just for polynomial solution. And just for the numerator of rational solutions, so now you have what we call a universal denominator. So you know the irreducible factors of the denominator, and you have bound VI. So you know the PIs and the VIs. And now you need to compute. So a rational solutions will be written like this: a polynomial p over this ui, this u of x that you know. How to compute p? Usually for differential equation, what you do is you perform a change of variable and you get an ordinary differential equations for p. Here, you cannot do this because of the integration term, because if you do this for integral differential equation, you will not get an integral differential equations for p of x. You can try to do it and you will see that you will have a problem. So an idea is to proceed as follows. You will consider a partial fraction decomposition of the rational solution, like this. So what we know are the di's and the xi's, and you want to compute the cig and the p of x. Of course, when you plug L of R of x in your equation, you will get linear equation for the cig's. Why? Because the logarithm terms, when you integrate, should vanish, and the term with negative valuation should also vanish, because when you apply L to a polynomial, you get a polynomial. So you will get many equations for the CIs. You solve, and then you will get an equation like this, where Q is a polynomial depending on some parameter. And here you need to compute polynomial solutions, just like before. Okay? And you can use the monomial by monomial approach. Okay? So that was exactly what I wanted to say. So we have developed algorithms for computing polynomial and rational solutions. These have been implemented in Maple. And as I already said, the perspectives are to compute larger classes of solutions, to consider systems instead of scalar equations, and many other things. I thank you for your attention. And if you have some questions, I can answer.
Thank you very much.
And sorry to be late.
Instead of 30 minutes, the duration of his talk was 42 minutes. So I suggest that we pose only one question.
Hi, Toma, it's Sergey.
Hi,
I
Sergey.
want to ask you about the upper bound for polynomial solution. Is it possible to use this upper bound as a low bound for formal Laurent series solution, for valuation of Laurent series solution?
Yes. For this, it's
possible.
the same as for integral differential equation. So you can use it as it is used like this. So you can.
Thank you once more for your interesting talk. We must proceed to the next talk. And the next talk is entitled On Rational Solutions of Pseudo-Linear Systems. The authors Moulay Barkatou, Thomas Cluzeau, and Ali El Hajj. Please.
Hello, everyone. Can you see my slides?
Oh, okay. You can start.
I think so, yes.
I see them, Ali. You can.
Okay. Okay, so first of all, I would quickly like to introduce myself. I am Ali El Hajj, a PhD student at the University of Limoges in France. On behalf of my supervisors, Thomas Cluzeau and Moulay Barkatou, I would like to present our new work on rational solutions of pseudo-linear systems.
I'm sorry, please enlarge your screen so that the full image on the entire screen. Okay. Can you please do this? A larger screen.
Sorry?
You are not in full screen, Ali.
Ah, sorry.
No, small, too small. Can you please magnify?
Okay, I'll try this.
Oh, okay. No, too small.
Yes.
Is it better? Is it okay like this?
Yes, it's okay.
Yes.
Okay. So first of all, let me start with a motivation example. So consider the problem of computing rational solutions of the following partial system in two variables, x and k, composed of one difference system in the variable k and one differential system in the variable x. The two matrices of the system, A and B, are matrices with rational function entries in k and x. For the computation of rational solutions of a difference system alone and that of a differential system alone has been widely studied before, and we can think of the methods of Abramov, Barkatou, Petkovchik, etc. The first step to compute rational solutions of our partial system is to choose one of these systems and consider the other variable as a parameter and use one of the existing methods to compute its rational solutions. So here I choose the difference system. I consider x as a constant parameter, and I find two linearly independent rational solutions given by the columns of the matrix W1. So now let P be the completion of the matrix W1 in a full basis. In particular, P is an invertible matrix having the columns of W1 plus a column vector V, an appropriate column vector V. We perform then the change of variable y equal P times Z. We will be reduced to solving the matrix linear system given here in red. The unique solution of this matrix linear system is given by this matrix N, which is independent of the first variable K. This is important. The third step is to consider the differential system in the matrix N. So this differential system only involves the variable X. And using the existing methods, we find that this differential system admits two linearly independent rational solutions given by the columns of the matrix W2. Finally, all rational solutions can be given by the product of the matrices W1 times W2. So what we actually did in this example is the following. We started by two systems having two variables. We get rid of one variable, and finally we were reduced to one system with one variable. And this is the main idea. However, we will be interested in this presentation in a more general case than in more than two variables, and in a more general system than just a system composed of difference and differential system. In particular, we will be interested in what we call a partial pseudo-linear system. So in order to clear up some confusions, let me first define what is a pseudo-linear system. So let C be a field of characteristics 0 and K be the field of rational functions in X with coefficients in C. Moreover, let phi be an automorphism over K and delta be a phi derivation. This means that delta satisfies the following rule. The constants of K are the elements A and C that satisfies phi of A equal A and delta of A equals 0. So now we are ready to define a pseudo-linear system. A pseudo-linear system over K is a system having the form delta Y equal M times phi of Y, where M is a square matrix with rational function entries in X. So pseudo-linear systems, in fact, is a very large class of linear functional systems, which includes the familiar differential, difference, Q-difference cases, and etc. And any of these familiar types can be written in the pseudo-linear system form. So now we are ready to define what we call a partial pseudo-linear system. So let K be the field of rational function entries in m variables, x1, x2, xm. A partial pseudolinear system is a system composed of m first-order pseudolinear systems, and the matrices of this system are square matrices with rational function entries in x1, x2, xm. We will assume that this partial pseudolinear system is integrable. This means that there are some conditions on the matrices of the system. And moreover, each system appearing here is considered as a system in one variable, and the other variables are considered as constants with respect to the corresponding phi and delta. So our main objective in this presentation is to develop a recursive algorithm to compute all rational solution of this partial system. So this in particular requires first an algorithm to compute rational solutions of a first-order pseudolinear system in one variable. Of course, this has been already done for the familiar cases for differential, difference, and Q-difference systems. But as far as we know, this has not been done to general pseudolinear system. So this will be our next contribution. So in order to compute rational solutions of one single pseudolinear system in one variable, we follow the classical strategy, which consists first in computing a so-called universal denominator, which is a polynomial that is a multiple of the denominator of any rational solution. Then we perform a suitable change of variable, and we will be reduced to computing polynomial solutions of the resulting system. These polynomial solutions can be computed using several existing methods. In our implementation, we use the monomial by monomial method developed by Barkatou, Broughton, and Flugel in 2010. So polynomial solutions will not be a problem for us. It has been already investigated. What we will focus on is the computation of a universal denominator of a pseudolinear system with one variable. So for a pseudolinear system, delta y equal m phi of y, we have two cases. Either phi is the identity map, and this corresponds to a differential system, and an algorithm is already developed by Barkatou in 1999. This algorithm uses simple forms to compute a universal denominator. Otherwise, in the second case, if phi is not the identity map, then our pseudolinear system can be written as what we call a phi system, phi of y equal by, where phi here is a automorphism that maps x into qx plus r, where q is not a root of unity, but if r is not 0, then q is allowed to be equal to 1. So differential systems, or the first case, is already investigated, so we know how to deal with it. What we will focus on is the computation of a universal denominator of a phi system. And of course, phi systems includes pure difference systems and pure Q difference systems. And these particular classes have been already investigated in the past. Okay, let me first give a review, me and this child, on this Q difference case. So, we will visit the work of Abramov in 2002 concerning the Q difference systems. So consider a Q difference system where phi is the automorphism that maps x into qx, where q is not a root of unity. A universal denominator of this Q difference system can be decomposed into two parts: x power alpha times u of x. Here alpha is a non-negative integer, and u is a polynomial which is not divisible by x. On one hand, x power alpha is called the fixed part. It can be computed using e.g. eliminations, as it is done by Abramov, or using so-called simple forms. On the other hand, the polynomial u is called the non-fixed part. It can be computed using resultant and GCD computations. So, now for a general phi system where phi maps x into qx plus r, as in the q difference case, a universal denominator can be decomposed into two parts. The first part is x minus r over 1 minus q power alpha times u of x. Here, alpha is a non-negative integer and u is a polynomial not divisible by this guy. So again, this guy here, the first part is called the fixed part, and it can be computed using forms. And the second part is also called the non-fixed part, here the polynomial u, and it can be computed using resultant and GCD computations. However, we have extended the ideas of Mann and Wright in 1994 and also the work of Abramov in 2010 to have a more efficient method to compute the non-fixed part. This method actually is based on the full factorization idea, and it has been proven to be more efficient in practice. So now until now we have completely solved the problem of computing rational solutions of first-order pseudolinear systems with one variable, because we have seen how to compute a universal denominator, and we already know how to compute polynomial solutions. So let us return to our main problem. We want to compute linear. This system is integrability condition. Operators of the system commute. Pseudolinear system is composed of pseudolinear systems, and all the matrices are matrices with the rational function entries in the variables x1, x2, xm. And each system is considered as a system with one variable, and where the other variables are considered as constant parameters. So the general algorithm that we have developed proceeds as follows. First of all, we compute a matrix W whose columns form a basis of all rational solutions of L1, the first system. Of course, if you do not find any non-zero rational solutions, then we are done with our original part rational solutions. Of course, you can choose any system, L1, L2, L3, afterwards, which choice to be made in order to have a better performance. So now if m equal to 1, this means we have one pseudolinear system. Otherwise, we solve the m-1 matrix linear systems having the following form, and we denote by Ni the respective unique solutions, and the matrices Ni are actually independent of the first variable x1. Next, we consider the following partial system composed of m-1 pseudolinear systems, and this partial system is free of the variable x1. And then we repeat the same process. So basically what we actually do here is that at each iteration of the system, we get rid of one variable, until we reach just one pseudolinear system with one variable. Finally, the product of the W's obtained at the first step of iteration will give us a basis of rational solutions of the original partial system. So let me clarify the algorithm with an example. Consider the following partial pseudolinear system. In three variables, x1, x2, and x3. The automorphisms phi1, phi2, phi3 are given here in blue, and the corresponding derivations, deltas, delta 1, delta 2, delta 3, are given here in red. And the matrices of the system, M1, M2, M3, are actually matrices with the rational function entries in x1, x2, x3. So first, we compute rational solutions of the first system, which in one variable, x1. We find that this system admits two linearly independent rational solutions given by the columns of W1. Now we solve the two matrix linear systems here in blue, in N2 and N3, and we find that N2 and N3 are the following matrices, and we can see that they are independent of the variable x1. Next, we are reduced to solve the following partial pseudolinear system with the matrices N2 and N3, and this partial system is free of the variable x1. So we repeat the same process. We compute a basis of rational solutions of the first system appearing. We get W2 here. The columns of W2 are rational solutions. Next, we solve the following matrix linear system. The unique solution is the following guy, and it's independent of the variable x1 and x2. And next, we will be reduced to solving the following first order pseudolinear system in just one variable x3. This system here is free of the variables x1 and x2. The latter system admits two linearly independent rational solutions given by the matrix, by the columns of the matrix W3. So finally, a basis of rational solutions of our original partial system is spanned by the columns of W1 times W2 times W3. So now we compare some strategies of our algorithm. Recall that at each iteration of our algorithm, we choose one system in order to compute its rational solutions. So the question is, are there some choices which are better than others from the computational point of view? We will answer this question by giving some timings of one of our experiments carried on several partial systems composed of one differential and one difference systems with two variables x and k. The matrices of our partial systems are generated from a randomly chosen fundamental matrix of rational solutions, but whose denominator is fixed as a product of some of the following three polynomials, u1, u2, and u3. So we compare two strategies. In strategy one, in which we start with the differential system, and strategy two, in which we start with the difference system. So the following table gives the timing obtained for computing rational solutions with each strategy, with different sizes of the system n, and with different fixed denominator u. So the table seems to indicate that strategy 2 gives, in general, a better timings. The difference between the distinct timings seems to be significant if the denominator includes large factors such as u2 and u3. In the case u equal to u1, there are no large factors in u1, and so strategy 1 behaves well. So going deeper into the analysis of this experiment, we noticed that most of the time in strategy 1 is spent in computing simple forms, which can be quite involved for large factors as u2 and u3. In strategy 2, there are no simple forms to compute a universal denominator, since we have a pure difference system. And thus, the large factors u2 and u3 will disappear in the next iteration, because the differential system that we will consider will only depend on the variable x. So based on this result and other experiments that we have performed, we always make the choice to treat the phi systems first and to consider the differential systems at the end of the iterative process. So I finish with some remarks on the implementations. So the recursive algorithm that we have developed to compute rational solutions of partial pseudolinear systems is fully implemented in Maple in our pseudolinear systems package. This package is freely available online. You can visit my webpage and have a look. There exist also several examples to cover several procedures in the package. The package also includes a generic procedure to compute solutions of a general pseudolinear system in one variable. And it also includes a generic algorithm to compute a so-called hypergeometric solutions of partial pseudolinear systems based on the same recursive idea. So thank you very much. Do you have any questions?
Thank you very much for your interesting talk. На русский язык перейду. Все равно здесь все это понимают по-русски. Может, один вопрос всего?
So thank you for your interesting talk. And my question is, what about higher order systems? You consider only first order systems, yeah?
I'm not hearing well. Can you repeat, please, Sergey?
Oh, sorry. So you consider only first order systems. So
yes.
It's correct. And what about higher order systems?
Higher order pseudolinear systems?
Yeah.
We have not studied this case. We have no expectations on what we could result in this investigation. But I think it's an open question. I cannot give you a clear answer to this. So maybe my supervisors know better than me. But I don't know.
We thank you once more for your interesting talk.
Thank you.
Now we proceed to the last talk in this session. The talk is entitled Horn-Kapranov's Uniformization and Systems of Algebraic Equations.
Я не знал. Ну, да, все слышно. Значит, презентацию, одну секундочку, Петр. Значит, почему мы ее не видим? Надо переключить там, да? Да, пожалуйста, если есть возможность. Okay, well, I will start very early, since we don't have much time, but I'll be quick, because I know that we have excursion and we may not be late for lunch, so please do not worry. And I haven't brought my daughter with me, so I'm on my own. And I'd like to start, as always, by thanking the organizers, the local organizers of this great place, the Sirius Center in the Olympic Park of Sochi, the director, Alexei Shuplev, and his assistants, Irina Klevtsova and Natalia Tokareva. They are doing a great job, and I'm very grateful for everything which they gave us at this workshop. Okay, so I guess I should be, yes, I need to see my presentation, but I will start gradually by telling that I will be speaking about solving algebraic equations and systems of such equations by means of the so-called Horn-Kapranov parameterization. Okay, so I need to have it in full screen mode, right? Ctrl L, yes, it works. And the clicker, yes, the clicker works as well, so thank you very much for the assistance. And I will begin by looking at the fundamental question, which has actually been brought up by a lot of different people at this conference, and I owe a lot to the earlier speakers at the workshop. And this is the single algebraic equation in any number of variables in the complex space. Just the very classical setup to begin with. And what I would like to do is to look for solutions to that equation in some sense, to be made precise later, and also to investigate its multiple roots. So the basic setup is as follows. I'm looking at a finite subset of the integer lattice. I denote by n its coordinality, and I'm looking at the solutions to that equations, and in particular, I am interested in the case when the equation has multiple roots, meaning that the gradient vanishes somewhere at the zero locus of the polynomial in the left-hand side. Now, the fundamental notion, which I like to base my talk on, will be that of the so-called A discriminant, which was introduced earlier, about 30 years ago, by the giants of the field, and can be found in many papers, and also in the book by Gelfand, Kapranov, and Zelivinsky on discriminants, resultants, and multidimensional determinants. And the definition is as follows. So once we have such an equation, we are looking at the closure of the set where that equation has a multiple root. And if that happens to be a hypersurface, then its defining polynomial, well, under some conditions, made precise here, is called the corresponding A discriminant. And of course, in multiple talks at this workshop, we have seen different elimination techniques. For example, in the problems stemming from celestial mechanics, when it was necessary to eliminate a variable by, for example, computing the resultant of a couple of polynomials. But in general, we do need, of course, more involved computations, and this leads naturally to the concept of an A discriminant. So to motivate, I would like to start with a few examples that are chosen to be as elementary as possible. So the simplest possible example, which is not totally trivial, would be the second-order algebraic equation, and the corresponding A discriminant of the configuration, which consists of the 3 points in the lattice, just 0, 1, and 2, would be the classically known discriminant of the quadratic equation. Now, likewise, if we look at this kind of subset of the z squared, so we see the set lies on two segments in the real plane, then the corresponding A discriminant is just the resultant of a couple of bivariate polynomials. And of course, the classical determinant of a matrix can also be treated as the A discriminant, which stems from such a bilinear form. So all this is, of course, classically known, so I just recall those concepts. And it is, of course, important to be able to compute resultants, discriminants, or generalized discriminants of high dimensional matrices, like tensors in high dimensions. But this is, of course, difficult. Of course, nothing can be done by hand in any reasonable setup. But still, even with advanced computer algebra systems, it may be difficult because of the combinatorial blow-up, which occurs almost in any direction. So just a few examples to mention. It is difficult to compute discriminants of univariate polynomials It is difficult to compute resultants of polynomials. Determinants are no exception. And of course, that was quite an important question asked by Israel Gelfand himself in the 90s. It was his challenge to actually compute and investigate the structure of the four-dimensional 2 times 2 times 2 times 2 hyperdeterminant. And that's a paper about this single object by Bernd Stolfis and his co-authors. And that was quite a task to perform this computation. Now, what I would like to do is this. I will illustrate this by means of a very simple example. I'll be looking at a matrix in 3 dimensions. So classically, and of course, totally well known, its determinant is given by this polynomial with 6 monomials. So we can, of course, dehomogenize the 0 locus of this polynomial by first dividing by, say, a11, a21, and a31, and then making a simple linear change of variables. So in reality, we are not 9-dimensional, but we can reduce the number of dimensions by the number of 5, and we're left with just 4-dimensional subspace in the 9-dimensional space of generic matrices of this kind. So we'd like to look at this kind of polynomial and investigate its zeros. So we want to solve the equation that is obtained by equating to 0 this polynomial below. Of course, we can solve for many variables. Still, however, I would like to argue that the best possible solution to the equation, if we can call it, would be the parameterization of its 0 locus, which is this. So it turns out to be possible to do this. If we replace A, B, C, and D by the corresponding homogeneous rational functions, then we plug in, we get 0, and there is nothing else there. So that is the perfect solution to that determinant. Now, the question which I was going to dwell on, but which I can't because I don't have much time, was whether it is possible to do this in general. And of course, the answer is yes, it is possible. So I will skip the technicalities and just proceed to results and question that I would like to ask. So what we'd like to do is to perform the same kind of computation for just any A discriminant. Yes, by the way, maybe somebody is aware of any software which already does this, but I'm not. I would appreciate any help. And the point with my talk is to propose a challenge and to ask a question. Okay, so it turns out that it is possible to do more or less the same in the completely general setup. We're looking at the complex torus. We observe the homogeneities of the general A discriminant stemming from a completely general finite subset of the integer lattice. We dehomogenize, just as we did in the case of 3 dimensions. And it turns out that if we choose a suitable basis, a unimodular matrix, which defines a basis in the kernel of the initial matrix A, then it is possible to obtain the parameterization, which is, of course, widely known as the so-called Horn-Kapranov parameterization of that 0 locus of the A discriminant. So the basic result, so I skip the theoretical part. So the basic result, the quote is the ingenious and seminal theorem by Mikhail Kapranov from '91, which states that it is, after all, that simple. So B as to B, why B is a suitably chosen kernel of the matrix A, gives the parameterization of the general A discriminant. Now, well, another example, now stemming from an algebraic equation, would be this. We take a look at the corresponding matrix, we compute the suitable kernel, and this is the object to deal with, the difficult one, and this is its parameterization, widely known by Kapranov's result. Now, what I did to present here, very briefly, was some computation by means of a piece of code in Wolfram Mathematica, some computation times, and concluding, I would like to ask the audience the following question and to propose the following challenge. So is it, after all, possible nowadays to produce a piece of code, an efficient piece of code, which would work stably and which would take just the configuration alone as its input and which would produce the parameterization of the corresponding A discriminant? Because, well, as far as I know, it's far too difficult to compute the A discriminant itself. So that's the question I'd like to ask, and I really have to be brief because at 10 minutes after 2, we have to get downstairs in the lobby to go for excursion. Please join. Everything has been paid for, and everyone is expected. So thank you very much. I hope I'm on time, and maybe there is time for one.
Also, thank you very much. Are there any questions or comments?
Am I right that the A discriminant is not expressed as a determinant of some matrix?
Well, that's in the GKZ book. In general, it is the determinant of a Cayley-Kashul complex, but it's quite difficult to construct. So theoretically, it is known, of course, but I would like to see an efficient piece of code to compute.
Any further questions or comments? No questions. Then let us thank the speaker once more for his interesting talk. You were able to present your talk within 10 minutes. And now everybody goes to lunch, and after the lunch we have a cultural program.
Коллеги, вчера кто-то телефон оставил.